Forging cyber security experts. Secure Ninja.
Hey everyone, I'm Alicia Webb with SecureNinjaTV. Now, our free preview of SecureNinja's online Sensei series has generated such a positive reaction that we've decided to give away every single module from this Cyber Kung Fu course featuring Larry Greenblatt, Tom Updegrove, and me. If you like what you see and would like to experience a Secure Ninja training course in person at any of our training locations, we have some amazing time-sensitive specials for you. Just visit SecureNinja.com/specials for all of the do not miss deals. And now, here is your free module from Cyber Kung Fu for the Certified Ethical Hacker version 8. Enjoy.
All right, in our next module, Sniffing, we're going to take a look at how we can use protocol analyzers to see what's on the wire. Now, we've already had a peek at these. If you notice, I have Wireshark loaded, and I highly suggest that people do start with Wireshark very early. So, for example, in your first labs in Module 2, you were doing ping and traceroute. I always recommend you have Wireshark loaded in the background and see how those things work. But let's now take a much closer look at how these protocol analyzers or sniffers work. Right. So taking a look at the OSI model, as we move down the stack, we have headers. So people create data, and then we know we have segment and packet headers. And now we have to talk a little bit more about those headers below and how that really works and how do we get access to the wire. So let me draw that up. And I'm going to use again, the 5-layer model that you see in the CEH books because I think it's fine for us. It really helps me simplify, not worry about presentation layer stuff, but really just get down to what's important. So I have an application, creates data, and the data will have to be addressed to be communicated and sent to the receiver. Now, I say it's like writing a letter, and you say to Alice from Bob, but you also have to say where Alice lives, you know, her address. So we talked about these headers that happened at the transport layer. And we call that a segment header. Again, that could be TCP or UDP. And the packet header added at the network layer to identify the source and destination machines. So what application, what IP address does this go to, and that's at the packet. And this is all nice to logically think things out, but that's not really what has to happen. We know that in order for these computers to communicate, you have to have wires, radio waves. There's got to be a physical connection. So at some point, there's something that knows how to talk to it, a network interface card, and it knows how to listen to a wire. Right? And they can share this wire and send information. So now I had to have a new address added. So at the data link layer, I have a new header stuck on this whole packet. I have a frame. Now, we'll just consider this whole thing the payload. We've got our packet segment. But in the frame, by the way, it's called a frame because it's the only layer that has a trailer. That could be important to us later. But this frame has the actual NIC's Media Access Control, or MAC address, because this is the media. How do I know when it's my turn to talk? I still find it amazing that this works. That, you know, in a series of seconds, I can get something from around the world, and my network interface card can look at those series of ones and zeros. So that's for me. But it does. It works. Now, media access control, how do I know when it's my turn to access the media? Originally, we wired things just like this, by the way. Our physical layer. Our physical layer is just cables and wires and hubs and stuff. Well, originally, I used to set up Ethernet networks like this. You would have a backbone with a 50 ohm terminator, everybody remembers that, and then you'd have this T connector, and everybody had physical access to the network. So before you talked, you would say, carrier sense, listen, is anyone else talking? Because I know there's multiple machines could be accessing this. but two people might try to talk at the same time. I need to know that, and that's it, collision detection. And that's how Ethernet was spec'd out. Well, these things were cumbersome to troubleshoot. We finally went to a very simple physical layer device, the hub. And the hub basically did the same thing, just made it easier for me to connect everybody in a star. In either case, if somebody sends a packet, say host A talks to host B, and I have a machine in here, I could see those packets. I would ignore them typically. But if I told my network interface card, don't just process things headed for my MAC address, I want to see anyone's MAC address. Remember, see, that's called promiscuous mode. Very important to understand if you're going to see other people's traffic. And I could do that here as well. I could load my sniffer here and see that. But then it became a little more challenging because these collisions, and this is the way it came up for me, they were normal, but they shouldn't eat up, well, we used a metric of 3%. If more than 3% of my traffic was collisions, we broke this up with a layer 2 device, the bridge. A bridge has intelligence. It knows how to look at the information in the frame header, basically the source and destination MAC addresses, and then make forwarding decisions. It's pretty cool. Let's draw that out. So now I could separate, and this is how we would do it in those days, my separate Ethernet buses with a bridge. And I have separate domains. Well, what it did was it would learn MAC addresses. Now, MAC addresses are 48 bits. We know that each hex code is 4 bits, it's 12 digits. I'm not going to draw that many. I'll draw 2. But 0A would, and 2B or F9, D7. When you first turned on the bridge, it didn't know these guys. But the source MAC address should always be unique. Destination could be a broadcast or a multicast. So it would learn these and say, I learned 0A on port 1. I learned F9 on port 2. I learned D7 on port 3. And it would maintain this in the very testable content addressable memory, the CAM table. All right. Now, the bridge's primary function was to make one of 3 decisions. If 0A wants to talk to D7, it will forward that from here to here. So it can forward traffic. But it would make no sense to send it to 2, so it would filter. That's its job. And there's never a reason to forward a collision, so we always know that our bridges, or our layer 2 switches now, create separate collision domains. That's a great idea. But if the destination MAC address is unknown, or if it's a broadcast, it's got to send it out every port. Actually, wouldn't if it came from here, well, I know this segment got it, so send it at every port except for the one it came in on. All right, and that's called the flood. Hackers noticed that they could sniff across this bridge by flooding the CAM table with spoofed MAC addresses. And it goes by many different names. Some people call it ARP flooding. Well, ARP is a very common packet. You'd see it all the time. It's a very small packet, and you could certainly do it with ARP. And the only tools I know, or at least the first tools I know that could do this, now there's a number of them, but DSniff and EtterCap and a number of other tools. They use ARP because it's very small. I've also noticed that people think this is then an ARP table. That's not an ARP table. Remember, the ARP table says, I know that 0A belongs to this IP address, 10.1.1.1. That's ARP. The CAM table is what physical port on the switch to what MAC address. Similar, but not the same. So one way to sniff across this for hackers is to just overwhelm the CAM table. I'm not a hacker. I was a network ops guy. I had to come up with another way to do this. Well, Cisco, now today we don't have bridges like this. We have a multi-port switch. Right? And we had, originally in the 90s, I had these 5500 catalysts, and you'd have, there were 13 blades, but we'd say 9 blades were populated with Ethernet ports. And between every port is a switch. So when I had to troubleshoot a server problem here, and it was intermittent clients getting to it, and watch out trying to be Mr. Smarty Pants because I usually get burnt. The call elevates to me. It's like, hey, Larry, we got somebody at Microsoft's on the phone about this FSO2 problem. It was a server guy. It wasn't really my problem, but he said he needs to talk to a network guy. And the network, it's an intermittent problem. And he said, can you get me a trace? And they want to be used, if anybody remembers, old Microsoft Network Monitor. And
Mr. Greenblatt, no cell phones in the virtual classroom.
That wasn't me. What? We could fix it in the mix, no? All right. So anyway, so I get the call, and a Microsoft guy says, do you have Network Monitor? It was a Microsoft sniffing tool, very nice tool actually. Could I do a trace of that server? Now it's an intermittent problem, so he wanted me to set up a circular log, something like, let's get 10 meg files. The 11th we'll rewrite over the first one, and then when we have a problem, let's take a look at that trace. I said, sure. And he goes, okay, and I'm all prepared. I'm going to plug my sniffer in here, and I know I can do Cisco spanning, right? So if I have my Wireshark in here, I can tell on a Cisco device, Cisco device, I can say span this port. It's very testable span. And the engineer says, sir, are you plugged into a switch? I said, yes, I am. And he goes, well, you're going to need to plug that into a hub. And he wanted me to unplug the server from the switch, put in a stupid 4-port hub or something, plug that in, plug my, dude, I'm not going to do that. He said, well, sir, then I can't help you. And I said, no, I have a Cisco switch. I can span that port, sir. It'll mirror that port. And he goes, I've seen where spanning doesn't get everything. And I asked my partner, Jeremy, I got Microsoft on the phone about that FSO2 problem. Yeah, and I said, he's telling me he's seen where spanning doesn't get everything. He goes, yeah, I've seen that. Ruh-roh. Let's go back to that last page, guys. This might not be a hacking thing, but it's a very important troubleshooting thing. I told you the frame is the only thing with a trailer. In that trailer is a frame check sequence. It's a checksum. If it's bad, spanning won't forward it. Spanning will not forward anything that was made illegally too big. It's not an attack, but they would sometimes do that. They're called giants, or too small, called a runt. Spanning doesn't get everything. Now, in my case, I didn't have to worry about another issue, but suppose I was running an IDS in here, and I'm trying to aggregate 100 megabits per second for 48 ports per blade over one thing. So spanning does not get everything when you sniff, guys. Your best way to really sniff to see everything on this device is to get a full duplex tap. Actually, I bought dual com taps. They're very affordable. I've got a couple of them. They're under $100. So when you want to sniff, switches make a challenge for us. And that's true in IDS as well. So, well, okay, I said the hacker could do one thing. They can overwhelm that switch cam table. And that's the testable concept. Now, they word it many different ways. They may call it port flooding. Well, sort of. They may call it flooding the ARP cache. It's not really ARP, it's the cam table. But this is still something new to me because I always thought of sniffing as a passive attack. I tell my card, just listen. But now if I have to do something to something first, it's known as an active sniffing attack. That's going to be very important to us. Another way to sniff, and it is, since we do know there's a ARP table, every time you boot up, let's draw a very simple network. Go out to the internet, I've got a simple router here, and behind that router I've got a couple of workstations. And let's say Bob's MAC address is 0A, Alice's is D5, and the MAC address on the router is whatever F1. Their IP addresses 10.1.1.0/24. We'll make the router .1. Bob will be .2. Alice will be .3. You need to know a MAC address when you write something. I only knew you by your IP address. That's what DNS gave me. So you yell down the street, ARP. ARP is a broadcast. Who has, and say I'm looking for the router. Who has 10.1.1.1? And the router sends me the ARP reply, which is a unicast directly to me. I am. If you didn't ask a question, you should not be getting answers. But computers are very vulnerable to this. Bob yells down the street out of nowhere to Alice, oh, unsolicited ARP reply, I am 10.1.1.1. So now when she tries to talk to the router, she's going to talk to Bob, but then she can't get out to the internet. He'll tell the router, oh, by the way, I am 10.1.1.3. Every time the router gets something for Alice, it's going to send it right to Bob. Bob will forward it on to Alice. This is a man-in-the-middle attack done by sending unsolicited ARP replies and poisoning someone's ARP cache. All right, so the two ways that we're going to go on this test and look at active sniffing, what we're talking about is either overwhelming the CAM table on a switch or poisoning the ARP table on a workstation. All right, let's take a look at our slides here. All right, so we see the OSI model again, and now we can make sense of that. I work with an application. I want to create some data. I want to send somebody something. But in order to do that, I have to get there. Well, I put in www.google.com, and my browser says www, that's port 80. Google.com, hey, I got to get a name server. DNS, where is that? I get the IP address, but then I have to, where's the MAC address? MAC addresses are stripped off at every router. Earlier we called those locally significant addresses. So again, if I'm sending a package to China and I hear a train right there, so maybe I put it on that train. That train's going to have to drop it off at a train stop. He's not going to take it to China. So that's kind of like my Ethernet. He's going to drop it off at the nearest switch. Then that train might get lifted off and it's going to get on a boat. Now the boat has a special address, just source and destination of docks. And that's what my PPP connection is going to do. These are locally significant addresses. I have to know the address. And I just yell down the street, ARP. But again, the ARP request is a broadcast. The ARP reply, a unicast, and there's no way to check for unsolicited ARP replies. One countermeasure I've heard of is to hard code ARP tables. Who wants to do that? But if your risk assessment says in your case it's the right thing to do, then you do it. But I certainly don't want to do that. Another thing I want you to consider too as we look at this OSI model. When we started our LAN protocols, the data link and the physical layer are really the same thing. Ethernet tells me what my data link frame header will look like, and it tells me what my cable connector will look like. Right, so they went together. There was no authentication. I just plug in and I'm there. But a wide area connection might be I am using at the data link layer the serial line internet protocol, but the physical is an RS-232 connection. So it was required that we authenticate. Now it's going to be important to us when we get to wireless. I just want to plant a little seed there that in wireless, I don't know who's listening to me, so we brought that concept back. We now authenticate data link to physical layer connections. All right, just planting a seed for later on. All right, so the official term for a sniffer is actually a protocol analyzer. I remember when that was a trademark term, but somehow Network General lost that. To me, it still sounds like calling all tissue a Kleenex, but that's what people are going to call it. Our objective is to understand, as I said, I was very used to sniffing as being a very passive thing. In fact, think about it for your IDS. You don't want to smell your traffic, so you generally don't even have a layer 3 address on the device that you're doing your sniffing on. But for sniffing against a switch or poisoning someone's ARP, that's active. I now have to do something. That's a term I've only heard on the CEH, makes a lot of sense, just get used to it. Sniffing across bridges or switches, and remember a switch can work at any layer, but if you just see the word switch, assume layer 2. It is a multi-port bridge. This thing is going to require that I lie to the CAM table somehow. Now I could just pretend to be your MAC address. So rather than overwhelm the cam table, I go, no, I have that MAC address. It might send traffic over there. But then the next time that you send a frame, it goes, oh, I just learned it back there again. And I understand it's not really a very effective attack. It might break it. It might be more of a DOS than anything else. But they've been actually sniffing against traffic. Now, somebody will sit there and go, wow, if somebody flooded my cam table on my switch where I work at this bank or this agency, we would know right away because of something we learned in an earlier module. The simple network management protocol would have sent me alert. But a lot of people don't look at their stuff. Did you ever know anybody who either ran out of gas or didn't get their oil changed regularly? And you go, how did you not notice that your oil, it's been 5,000 miles and your car wants it every 3 or whatever? So some people don't look at their stuff. Sniffing wireless is a bit of a trick because they've encrypted it. But, well, they can crack encryption. Now, our crypto module is officially module 19, but I always ask students to watch that early because it makes password cracking so much easier to understand. It makes the defenses against session hijacking so much easier to understand. It makes sniffing this module so much easier to understand. So many things really are better understood if you watch that crypto slide show first. All right, so in wireless, and we'll have a dedicated module this later, but we have WEP, the wired equivalent privacy, where they encrypted traffic. Well, they chose a weak version of an algorithm, 40 bits of RC4. Keep in mind, we threw out DES at 56 bits in 2002 because it wasn't strong enough. Why would we do 40 bits? And they had a couple other flaws in there too. One of the major flaws, and we'll cover a lot more in wireless traffic, but we use encryption to both make something confidential and to authenticate. Never use the same key for both. All right. WPA and WPA2 knew that. It's a lot harder to sniff those traffic. You're not likely to crack the algorithms. You're more likely to just do a dictionary attack or some type of password crack and grab that. So. All right, so again, we know our network addresses. We have the globally significant information. So again, I know when I set up a connection to, I type in www.google.com. And a DNS server is going to give me the IP address. And then the browser assumed, well, if it was in this case, an SSL server, 443, if I said HTTPS. But how do I get the MAC address? Because this is really the field that has to be on the envelope. This is the thing that the mailman cares about. So it's a broadcast. Now these MAC addresses, and I have an example here, you can see that it's actually 12 digits, but these are actually handed out by the IEEE, the Institute of Electricians and Electrical Engineers, and given to vendors. It is sometimes called the vendor ID or the organizationally unique identifier, the OUI address. You can override these. In fact, in my experience, there were two things that showed me you could override it. DECnet in the 80s always did that on purpose. So anytime you put a network interface card into a digital equipment thing, it always started off with AA. But it was actually an issue when, in my experience, in about 86, IBM released a bunch of token ring adapters, I think it was, that had the same MAC address. So we were using Novell in those days as our network, but Novell came out with a command line tool to change your MAC address. But that doesn't normally happen. People use MAC addresses as security, and it's not a bad idea. We're going to, and it's quite testable to know in this module, that I could use MAC address filters on the actual switches, and they're known as port security. And port security comes in a couple of different flavors. I could say just this MAC address, or just this range of MAC addresses, or only allow one simultaneous MAC address, so somebody doesn't try to like plug a switch in there, or a hub in there, I should say. But people can override them. So it might keep honest people honest. It's not going to stop anybody who knows. In fact, you have a tool in your kit, I believe SMAC is the one they want you to use, but there's a bunch of them out there. All right, so in this case, this workstation wants to talk, say, this Internet Explorer browser wants to go to this Outlet web access exchange server. It's going to first have to ARP for the MAC address of this default gateway. That default gateway is going to have to somehow get the MAC address of this gateway, and then this one's going to finally he'll ARP down here. So this is why a man-in-the-middle attack could work. If I could get a machine here, I could send unsolicited ARP replies to this server, pretending I'm this gateway, and vice versa. And you can do that with a number of tools, and I believe in your labs you'll probably be using Cain Enable, and Tom has already introduced you to Cain Enable. It's a very, very powerful tool. I heard him call it the Swiss Army knife. So many tools get that name. Most people will say that about Netcat, which you also have labs for, but I totally agree with Tom. I think Cain Enable's got me a lot more tools. All right, let's move on here. So this will be the opening of Wireshark, but we have it here. So let's just launch Wireshark. Gerald Combs just released a new version, so we just got our 1.87 just came out. Now, when you open up, you'll have your interface list, and I can see that up here as well. I can go to my interfaces, and something really neat happened in 2013, guys. I can click on multiple interfaces, sniff at the same time. That's really cool. Way outside the scope of this class, but that is something that's very important. I can see I have an IP address on this adapter. There's packets being processed, so I can start sniffing that. Rather than do that and perhaps come up with something I'm in a hotel that maybe we shouldn't see, but I close that off and just bring up the capture I just did. All right, so first thing I did was I wanted to get an IP address. So I did that with DHCP, but unfortunately, there's no filter for DHCP. DHCP came from boot P. There we go. So I do a boot P, and it's the same port numbers. And don't worry, Gerald Combs and the other Wireshark people hear about it all the time. Can't you call it DHCP? Well, whatever. All right, so I can see the DHCP, and this is how I got my IP address. And that's going to be very important to us. Most people do not configure their own IP addresses, right? So if you're in an organization and somebody's claiming to be a certain IP address, ask the DHCP server, hey, DHCP server, you know this MAC address? Sure. Because DHCP works. Here's my MAC address. I need some IP settings. Ask that DHCP server, do you know him? Yeah. What's his IP? It's this. Oh, he's lying to me. That's the very testable DHCP snooping configuration. I only know that Cisco supports it, but there are command line questions on the test. All right. So you want to know how to have your switch query that DHCP server. And DHCP snooping says, give me that list of MAC addresses to IPs that you gave them. And then I tell the switch when somebody, and I said typically these tools use ARP, where they send an ARP with a spoofed MAC address. You say, do you know this MAC address? Yeah. What IP address did you give him? All right, I know he's lying to me. And that's important. It's dynamic ARP inspection. So 2 commands really required to make that work. All right, so now that I got an IP address, the next thing for me to do was to find my gateway. So I ARPed for the gateway. And I said, who has 2.1? Please tell me I'm 56. Now, if we look at that, I said that the destination MAC address you can see is all ones. It's a broadcast. This is the reason we really had switches, or excuse me, routers in the first place, to stop these broadcasts, because that was a lot of traffic. All right, but the ARP reply is a unicast. This is it. Now, you have your packet crafting tools. I showed earlier Packetizer. I mentioned you have in your toolkit Colosoft's Packet Builder. On your test, historically, they want you to know about HPing. HPing 2, again, is a packet crafter. HPing 3 is a scripting tool you use with it. So you could easily send an unsolicited ARP reply and pretend to be somebody else. Give them a different MAC address. Give them your MAC address. All right, but I got now the IP. Okay, so then I asked the DNS server, does anybody know where Google is? And I got a reply, yes, Google's IP address would be, and I should have a DNS reply. Oh, there we go, sorry. No such name, oh, that's a great one. All right, so, boy, that's pretty funny, no such name. We might want to look at that later. But we would get reply, here we go. All right, so we got a response. It's at 131 dot whatever, okay? And then I could look at how I connected to Google. Now, what's kind of cool is I could type in a long capture filter, and you'll need to know a couple. But let's say tcp.flags.sin equals 1. It's a very common filter for me. I use it all the time. I don't like typing it in, so I can save that. I can give it a name, and I've actually already saved that, and I just call it sin. So now I could look at all the sins. Now suppose I wanted to see a sin and an act though. Let's go look at what that really looks like. Here's my flag, sin and act. So when I look at those flags, I see the act set to 1. I see the sin set to 1. But if I look at that value in hex, it's 1, 2. So my flags take up, well, actually 2 bytes. But I'm not really looking at these first ones. So the last, let's see, 1, 2, 3, 4, that's this octet, or this hex digit 2. 1, 2, 3, 4. And then 1, 2, 3, and I'm not really looking at this. So that's a 1. So I could actually say TCP flags equals 0x means the following number is going to be hex. And I'll say 0, 1, 2. And let's apply that. And now I got all my sin x. So there's a couple ways to do that. I could do the hex, couldn't I? Might be important in your near future, I'm just saying. They will ask you to do a couple of Wireshark display filters, and that's what we're doing here. There's other filters you could create. When I set up a capture, I could decide to do a capture filter, right? I'm sorry, capture files. Let me get my capture filters up here. My problem with capture filters, though, is I may decide I needed that traffic. Yeah, because that would suck if I actually, oh, I didn't capture the ICMP and I needed that. I thought I was just watching TCP connection. So generally when you're capturing, if you have the space, try to capture everything, but I don't want to capture myself. So one thing I like to do is say not ether host and then put in my MAC address. So I don't want the dog smelling his own dirt. Another way to do this is to go to your network card. Now, of course, IP isn't the only thing you're speaking, but I may quickly just do something like this. If I turn off IP, I at least won't see any of my IP traffic. But remember, there's other things going on there, right? All right, or you can get a card that will process all traffic without loading a layer 3 address, like the Air PCAP card made by Riverbed, same people that govern the Wireshark project as well as their aggregator Cascade Pilot. So now I have one of these plugged in, and if we look at our interface list, you're going to see the Air PCAP adapter doesn't have an IP address. I don't want to smell my own stuff. So again, you could use a not my Mac filter, the only capture filter I ever use, or get a card that just doesn't load those addresses. Look at also that these, the number of packets processed by the Air PCAP card versus the Microsoft adapter. Why am I seeing so much more? Well, promiscuous mode is part of it, but there's something else, and we're going to need to know that more in the Wi-Fi chapter, but you also have to understand monitor mode. Monitor mode sees lower level frames that we don't need to do as a user, but the radio devices, the access points, and the other access clients need to know about. We'll need to know more about that in the wireless chapter. All right, so we're getting back to our slideshow here. Whoops, past that. Sniffing is when I load a card in promiscuous mode and process all traffic. Now, passive sniffing I mentioned is what I was used to, but again, active sniffing requires I do something. So if I'm going to sniff against a switch, I have to do something to its cam table. I mean, legally, what we want to do is use like a span port. We know that doesn't happen. Full duplex tap's probably a better solution. But hackers do it that way by lying. And they also do it by flooding the cam table with spoofed MAC addresses. ARP poisoning, again, is against a particular workstation. And if I just duplicate your MAC, sometimes called port stealing, I duplicate it, I spoof your address, I might get some of your traffic. You know where also this might be interesting? People do MAC address filters, say, on their access point. Well, if I could sniff out what the MAC addresses are, I might be able to just add myself to that filter. So pretty easy to do that. Packet capture tools, when I started out, you had hardware protocol analyzer. In fact, the first one I remember seeing was Network General Sniffer. It was a compact portable, but it was really expensive. I don't remember exactly. It was like $15,000 or more. And the hard part was getting the wide area network interface cards. Not everybody supported promiscuous mode. It was a big deal. But now, I started out with Ethereal, now called Wireshark, free, and it's probably the best developed, best maintained protocol analyzer out there. So besides being good for your test, needing to know how to do filters just so you can pass it, this is one of those tools, to me, must have. Capture filters, when I just only want to see certain traffic, I might do that. I told you I always filter myself. Display filters, that's probably a lot more useful. This is, I have a big capture, now just show me IP, just show me ICMP, show me the DHCP. And the 3 filters you'll need to know probably IP source, IP dest, and IP adder, and these will help me pick out a particular IP address depending on source, destination, or in either direction. All right. This is an aggregator tool. They introduce it in your slides. This is made by the same people who make Wireshark. And I like to say that staring at my network with Wireshark is like watching a football game with a 30,000 power telescope. Now, I can make out every pore on the quarterback's nose, but I won't know the score of the game. So really what I like to do is sit back and just show me my top talkers, my top protocols, my top conversations. And then when something looks suspicious, then I can drill into it. So for example, this is a capture of my house. All right, I went out for a day. I just decided to capture all the traffic with the full duplex tap coming into my house. And no one was home, and I've got a few machines that are loaded, and I see a lot of web traffic. Well, this could be, you know, my machine's talking to Norton, getting updates, maybe Microsoft, I don't know. Google's loaded, refreshing. Unknown, oh my gosh, what is that? All right, I drilled into it, turned out to be I have IP video cameras, and I go, oh, okay, Larry, those are your Panasonic cameras, all right. Email, remote desktop. I do not support remote desktop. So I highlight that, and I send it to Wireshark. And I see, and then I started checking it daily, about 4 or 5 times a day. This was about 2010. Somebody was trying to remote desktop in my house with a source IP address of China. And I started getting paranoid. I was like, what, somebody in China know me, want to get in there? And I talked to Tom, and Tom does a lot of this work. But when Tom's not teaching, he's supporting people's networks and troubleshooting these real problems. And he goes, let me guess, remote desktop. I was, yeah. And he said, yeah, it's not you, Larry. Nobody's targeting you. It's not. It's a tool. It's one of the latest attacks. They're scanning everybody to see if you get remote desktop on it with default credentials. Oh my gosh. So these are the things I can do now with Pilot. I can look into it. Anything that's clear text is vulnerable to sniffing. Right, so you can easily sniff out a clear text password, and we still see them in POP3. We still see them in SNMP versions 2 and below. We see them in default HTTP or web authentication. A lot of things are still clear text. Amazing. In fact, I sniffed out a spanning tree update, and I was, oh my gosh, the spanning tree could authenticate, but that's clear text too. So it doesn't really matter. You'll need to know some of these protocols. FTP, please know that Telnet, FTP, all your Unix remote, like our console, our shell, are all clear text by default, and you're going to replace those with encrypted versions, particularly SSH. Right? Sniffing defenses, always encryption. Physical security, don't let people plug in. Now sometimes it's like they're not plugging in, they're wireless. Where is this thing coming from? Well, I'm going to show this a little bit more in the wireless section, but MetaGeek makes an adapter. It's a spectrum analyzer, and they later came out with a direction finding antenna, and it can help you find some of this rogue infrastructure. Pretty cool. Port security. I mentioned I can lock things down to certain MAC addresses or a range of MAC addresses. We know we can spoof MACs, but it's a step. DHCP snooping, fantastic. And I take pride. Tom Updegrove, I'm not sure exactly how to pronounce it. Tom Updegrove, he's the creator of AirCrack NG, a tool you'll need to know for your test, was introducing his wireless intrusion prevention system last year at a talk at SharkFest. And I asked, will this have the feature to do like DHCP snooping, where I can query a DHCP server and make sure that that MAC address really does belong to that IP address? And Thomas goes, it will now. All right, so that's our sniffing lab. Hopefully that will help you understand how IDSs work as well. Remember, they're nothing but sniffers. So, Alicia, is there any questions on that module?
Good. Awesome. Thanks a lot, Larry.
Oh, you're welcome. And that's all for this module.
Now we hope you've enjoyed this free module, but there's lots more. The Cyber Kung Fu course has 29 videos in all and will really help build you a solid understanding of the CEH version 8 curriculum. Don't forget, if you prefer to attend one of Secure Ninja's courses in person at any of our training locations, you really need to visit SecureNinja.com/specials for some amazing discounts and other deals. I'm Alicia Webb. Happy training.
Secure Ninja TV is brought to you by SecureNinja.com, a world leader in cybersecurity training and certification. Our master instructors will help build you into a highly skilled and marketable security professional. Secure Ninja, forging cybersecurity experts.